Okay, so good evening everyone. Welcome to your 8th discussion session in Mechanical Behavior of Materials. Just give me a second. Welcome to your 8th discussion session in Mechanical Behavior of Materials. I am Pragyandipta Mishra, research scholar from Department of Applied Mechanics and Biomedical Engineering at IIT Madras. And today we'll be talking about critical resolved shear stress followed by interaction between dislocations and what happens to dislocations near the surface, and finally about partial dislocations. After that, we'll be solving a few problems on the same topic. So let's begin with today's discussion about critical resolved shear stress. So, why exactly are we studying about this value of critical resolved shear stress? What exactly are we trying to accomplish here? Now, any dislocation that is present in any material system or any single crystal system, let's say for instance, will require some amount of energy for it to start moving, right? Because dislocation by itself will not start moving until there is some barrier that is crossed. So how do we quantify this barrier? How do we quantify that energy value so that we can say that when it crosses this threshold, we will be sure that the dislocation will be able to move after this. So this value is given by this critical value known as critical resolved shear stress. And why we are quantifying this as a stress value is because in most of the concepts that we have studied till now, we use stress as a measure to measure strength, right? Rather than using energy or force. We use stress as a measure because it gives us a quantitative indication of as to for a given area, if this many dislocations are present or this dislocation is present, then we will get this value of stress that is required for this dislocation to move, right? So what is this critical resolved shear stress? Or rather, let's start with what is resolved shear stress, right? This is the minimum value of shear stress that must be applied for dislocations to move, right? Like I said, this gives us a threshold, the threshold value of shear stress that has to be applied for any dislocation to start moving. Now, how do we quantify this? Say, for instance, we have a cylindrical body like this. Let me just draw it. Okay, a cylindrical body like this, and let's say I'm applying a force P on its top and bottom. Now, if there is a plane that is located at some angle, okay, let me use a different thing. Say there's a plane here, okay, that is not parallel to the top and bottom face. Okay, this plane is not parallel to the top or bottom face. It is, let's say that the normal to this plane, okay, is inclined at an angle phi from the normal or from the load direction, let's say, because load is acting on the top and bottom faces or parallel to the top and bottom faces. Sorry, perpendicular to the top and bottom faces. So if we take an angle from the load direction, it is acting at an angle phi. The normal to the plane is acting at an angle phi from the load direction. And let's say that this is the plane on which the dislocation will move or slip will occur. Okay, we know that slip is basically dislocation moving, right? So this is the plane where the slip will occur. So we call this plane as slip plane. Now, in which direction will the dislocation move? Let's classify this as some random direction. Let's say I am taking some direction here in which the dislocation is moving. Okay, so this is my slip direction. Now let's say this slip direction is inclined at an angle lambda from the load direction. Okay, so can we find what is the effective value of stress acting on this face, acting on this dislocation rather, for this for slip to happen, right? What is the effective value? So first let's note it down again. What are the things that we have seen on the figure? Phi is the angle that between the normal to the slip plane and the loading axis. Okay, lambda is the angle between the slip direction, right? Slip direction and the loading axis. Again. Okay. So now we want to find shear stress, right? We want to find shear stress. So we have the load. We can find the component of the load along a particular direction, but we cannot find the component of. We also need to find the area, right? Not just the load. So area here is, let's say that the area of this at the top face, basically this face was A, and this area here is A dash. So how can I write A and A dash? How are they related? So if you think about it, A and A dash are related.
It will be like 8 divided by cos phi.
Correct. So basically A dash is tilted by an angle phi, or A dash, or rather A dash normal is tilted by an angle phi. So A dash times cos phi would give us A, right? So this is one relation. Now similarly, if this force P is acting along the top face, along the slip direction, what would be the component of that force? It will be just P cos lambda, right? Because for the area, so I'll put it here so that there is no confusion. So this will be P dash, right? I'll drop this out. This will be P dash in the slip direction. So what is the relation between P dash and P? P dash will be equal to P cos alpha, P cos lambda, right? If you see the geometry, P dash and P,
Yes.
there's an angle of lambda in between them. So it is P dash. So P dash is tilted by an angle lambda from with respect to P. So it is P cos lambda. Now, if we want to find the resolved shear stress, mind you, I'm not talking about tau CRSs. I'm talking about resolved shear stress, not critical resolved shear stress. Tau R. Okay, we call it tau R. That will be equal to P dash by E dash, because we are talking in terms of the slip plane and slip direction. So P dash by E dash, so that will be P cos lambda divided by A divided by cos alpha, cos phi, sorry. So if I take everything to the numerator, it will be cos phi cos lambda. Now P by A is what? P is, if P is acting on the top and bottom faces and A is the area of that face, then it is just the tensile stress, right? Or sigma. So sigma cos phi cos lambda is my resolved shear stress, right? So this is how we can find the resolved shear stress for any component, right? Now there are a few things that we need to understand regarding this resolved shear stress, right? First thing is that this resolved shear stress and N, sorry, resolved shear stress dot N. So what is N here? Does anyone know what is N? N is normal to this place. Okay, I have not noted it down. So tau R dot N and P need not lie on the same plane. Okay. What that means is essentially we need not have phi and lambda adding up to 90 degrees. Okay. Essentially that means, so this is a more mathematical way of saying tau R dot N, because tau R is acting along the slip direction, N is perpendicular to the slip plane. So tau R dot N and P, if tau R dot N is like giving, like is in the same direction as P, then we will say that okay, they are lying on the same plane. So but it need not happen. Okay, so this would mean that phi plus lambda need not be 90 degrees. Okay. So also another thing is that lambda also need not be 90 degrees. Okay, these are special cases which can only come when you are aligning it along a particular direction only. But in general, this need not be the case. Okay, so you don't have to think that this is the only case. So now that we have talked about resolved shear stress, what do we mean by critical resolved shear stress? What is the reason why we want to move from resolved shear stress to critical resolved shear stress? So what did I define CRSS as earlier? It is the minimum value of shear stress that must be applied for dislocation to move, right? So what does this remind you? It is like a threshold value, right? Like a yield value, right? Like yield strength was a threshold value. So this is something like yield strength. It's not exactly yield strength, but it is like yield strength. For single crystal, okay? So when do we say we are talking about resolved shear stress, and when do we say we are talking about critical resolved shear stress? So there are 2 points to note here. There, the resolved shear stress will act whenever a load is acting on a body. So the moment you put load on a body like this, along the plane, along the slip plane and slip direction, you will have a resolved value of shear stress. But that only when that value exceeds a critical value, then only the dislocation will start moving. Okay, so you will always have resolved shear stress if there is force acting, but that value should exceed a value known as critical resolved shear stress only only then the dislocation will start moving. Okay, so let's write out the first point. If tau r is less than tau CRSS, okay, tau CRSS is the critical resolved shear stress. Tau r is resolved shear stress. Then there exists shear stress on the body or on the crystal, let's say, because we're talking about the crystal, right? A single crystal. On the crystal. Okay. There is stress on the crystal, and consequently on the dislocation. Okay. Essentially, if there is stress on the crystal, that stress will somehow be transferred to the dislocation. But if it is lesser than tau CRSS, dislocation does not move. Okay. Now, then how do we differentiate between tau r and tau CRSS? Essentially, tau r is a variable quantity. It's not a fixed quantity. Tau r is a variable quantity. Which depends on applied stress, geometry, orientation, etc. Right? Okay. Orientation. On the other hand, CRSS is more like a fundamental property, a threshold, because it's defining like yield strength, right? It's like a fundamental property that is associated with the material. Okay.
Sir, suppose there are certain heat treatments which can change the elastic modulus of a material. So
Right.
will it affect this tau CRSS?
So if it is affecting the phase, within the material system. So if the phase undergoes a transformation, then there will be a change in the tau CRSS value. However, if after the heat treatment you are getting back the exact same phase which you had earlier, then there should not be any change in tau CRSS. I hope that's clear.
Okay. Yes, yes.
Therefore, this tau CRS's value becomes a very unique and useful quantity when we are talking about dislocation, when we are talking about plastic flow, plastic behavior of any material system, because it is a singular quantity, a constant, a material property that we can identify for a particular material system, and then we can make like claims about a material behavior and how the material would behave and all that, right? So therefore, tau CRSS is more like a fundamental material property that can be quantified or measured by using like different techniques, experimental techniques. Okay, so this is about tau CRSS, right? Now, if you remember, we had also talked about earlier, like about Piles-Navarro stress, right? Tau PN. So Piles-Navarro shear stress was also quantifying the stress required to overcome lattice resistance, right? So let's talk about how these two quantities are different. Okay. So essentially, both of them are representing like a threshold value, a minimum value that you need to overcome for any lattice resistance, right? How are they like? But then, what could be the major difference between these two? So first, let's write down what is the common thing between them. Just have a few pictures. But when we defined Piles-Navarro shear stress value, we talked about it being a theoretical quantity, right? And we talked about like specific conditions like 0 Kelvin, etc. So it is more like a theoretical value that has been defined for a particular material system. However, that value does not always yield the correct result when we are looking at the actual or real life experimental conditions. Okay. So the major difference is tau PN is theoretical. Okay. And defined at 0 Kelvin. While tau CRSS is experimental and you can obtain it for any given temperature. So essentially, if we are checking the tau CRS's value at different temperatures, you will get different values for the same phase. Okay. Why that will happen is because dislocation motion will become easier. Glide will become easier sometimes. Climb will become easier as we increase the temperature. So tau CRS's value will get influenced by temperature to an extent. However, tau PN had no correlation with the temperature. So there was like we will say that it is obtained at 0 Kelvin, and that's like a theoretical value that we can say for a particular material system. Okay. Now let's talk about what could be like a range for this uh, cos phi cos lambda value. Okay, so essentially, since we said that this tau CRSS is fundamental material property, what we need to find is how this tau R has to approach tau CRSS is basically dependent on the sigma value that we are providing. That is one thing, but also also the geometry and the orientation. Right now, geometry is something that we cannot control, right? Because it is basically the shape in which we are getting the material or whatever material system we are provided with. So the two things that we can control is one is the load that is being applied, so that we can reach that tau CRSS value. The other thing that we can change is we can change the orientation, right? So if we can change the orientation somehow, maybe we can affect how much load that needs to be applied in order for us to reach that tau CRSS or particular tau R value that we need to reach, right? So let's say tau R is equal to sigma cos phi cos lambda. Now this quantity can be also represented by M, okay, which is Schmidt factor. So what we want to do is influence this Schmidt factor value somehow, so that we can tweak how much sigma we need to apply in order to get some tau R. Okay. So if M value, like if from this relation you can see that if M value will reduce, then sigma value has to increase, right, for the same tau R, and vice versa. So essentially, for maximizing Schmidt factor, for maximizing Schmidt factor, or rather, maximizing Schmidt factor would result in a reduction in sigma value, and in order for us to do that, we need to have phi and lambda to be minimum, right? Why? Because it's cos, right? Cos of something. Sine of something is more like an ascending from 0 to 90, right? But cos of something will be descending. It goes from 1 to 0. If you go from cos 0 to cos 90, it goes from 1 to 0. While sine goes the opposite way, right? So we need to have minimum phi and lambda, while cos phi into cos lambda should be maximum. So if we plot this out on a curve, let's say phi is equal to 90 degrees to phi is equal to 0 degrees. If you're plotting it out, then what we will see, like what people have observed using experiment also, like they have conducted experiment for different material system. What they found out was the M value actually went like this. Make it a little more even. Okay, so this is M. So the highest value occurred at 45 degrees. Okay, so this is M. while at the same time they observe that the sigma value that is required to reach, so this is sigma, let's say I'm plotting sigma value that is required to reach a particular value of tau r was the least at 45 degrees, as you can see from the equation itself, right? Sigma is equal to tau r by m. So if m is maximum, sigma would be minimum for the same value of tau r. So essentially, what we are saying, that condition that I talked about, right? This condition that I talked about here, tau r dot n and p need not lie on the same plane. So this condition gets fulfilled here. Essentially, you will have tau r dot p, tau r dot n and p lying on the same plane. That is phi plus lambda is equal to 90, or more importantly, phi and lambda are both 45 degrees. Okay, so that is like a very, very unique case when phi and lambda are both 45. Not just phi plus lambda being 90, but phi and lambda are both 45. So we have seen that phi plus lambda should be equal to 90, right? Now we want to also show that phi and lambda are both 45. How do we show that? Now m is equal to cos phi cos lambda. Now phi plus lambda is 90. So I can write cos of 90 minus lambda as phi, right? Cos lambda. The cos of 90 minus lambda is sin lambda. Cos lambda. Now that is equal to sine of, or half of sine 2 lambda, right? Sine 2 lambda by 2. Now when is sine maximum? Sine is maximum when sine theta is maximum when theta is equal to 90, right? So 2 lambda should be equal to 90, or lambda should be equal to 45, which also implies phi should be equal to 45, as phi is 90 minus lambda. So essentially what we are saying is when lambda and phi are both 45 degrees, we will have the like the lowest value of sigma. So this orientation is known as soft orientation. Okay. Essentially, why it is called soft orientation? Because you need very low value of stress for yielding to start. Okay, for flow to start. While you will see that at 0 and 90 degrees, you will have very high values of sigma required for yielding to start, right? So they are known as hard orientation because it is very hard for us to, or more value of stress is required to overcome the yielding, overcome the flow stress or yielding to occur, right? So let's just write it. Orientation close to 0 or 90 degrees are hard orientations. As high stress is required, high value of stress is required high value of stress is required for yielding. Whereas orientations close to 45. Close to 45 degrees are soft orientation. As no value of stress is required. For yielding. Okay. So this is about CRSs, resolved shear stresses, and critical resolved shear stresses. So now, next we want to talk about is interaction between dislocations. So how do we try to talk about these interactions? We'll talk about these interactions in a way that we have one dislocation or we have a family of dislocation, how that influences another dislocation. That is how we'll talk about interaction, okay? Rather than talking about each dislocation affecting every dislocation, because that will be very difficult for us to keep measuring if we are just measuring each interaction separately. What we'll do is we'll take one dislocation, say this is one dislocation, dislocation 1, how that is affecting another dislocation, dislocation 2, how this is affecting. Okay, dislocation 2 is what we will be concerned with. Okay, so now this dislocation 2 could be present at any place with respect to dislocation 1 in XYZ, right? In any place it can be present. The coordinate can be anywhere. We will look at how that affects dislocation 2. Similarly, we could also have like a cluster of dislocations. So all these dislocation together, how they influence another dislocation also could be studied. Okay. So essentially, every time we'll be studying with respect to dislocation 2, how this one dislocation or a cluster of dislocations is affecting another dislocation. Okay. So essentially, this interaction would be how much external force is needed for dislocation 2 to overcome internal resistance. Okay, that's what we are concerned with. So this interaction is given in the form of an equation known as Peach polar equation. Okay, so let's talk about Peach polar equation. So this Peach polar equation gives us a force F, okay, which is equal to sigma 1 times or rather let's just write it as sigma. Sigma times B1, B2, sorry. B2 sigma dot B2 cross epsilon 2. Okay. So this force gives this F gives me the force per unit length at any point for dislocation 2. Okay. So let's just write down what each quantity is. So F is force per unit length at any point on dislocation 2. Sigma is stress experienced by dislocation. B2, as you would have already guessed, is the Burger's vector. Right? For dislocation 2. While epsilon 2. Now what could epsilon 2 be? If we have already talked about the Burger's vector associated with the dislocation, what is left then? We have talked about the Burger's vector, which is a slip vector. Then which is the only other vector left where the stress would act for any dislocation? Line vector, right? Dislocation line vector. So dislocation has a particular line. So along that line also the stress will act, right? So it will act along the Burger's vector and along the line vector. Okay. So if we are able to find these individual quantities, we can find the force per unit length. Okay. So essentially, what we are having is something like this: force is equal to, if we can get sigma xx, sigma xy, sigma xz. Okay. So essentially, all the components: y, yy, yz, xz, yz, and z. This will be all the components. Now I am dotting this with bx, by, bz. And finally crossing the whole thing, this whole thing. Okay, then finding the cross product with epsilon x, epsilon y, epsilon z. Right? So I will get fx, fy, fz. So how will that f look like? If I expand and write final f, it will look something like this. Sigma yx bx plus sigma yy dy plus sigma yz bz whole into epsilon z minus, okay, this is too big. Let me just write it a little bit smaller. One second. Yeah, let's write it a little bit smaller. Sigma yx dx, yy dy, and yz dz. Right? Minus sigma. Then we write in terms of x. Zx dx sigma zy dy plus z z bz times epsilon 1. Right? So this is one term. This is fx. Similarly, we'll have fy and fz also. So this will be sigma zz zx bx sigma zy dy plus sigma zz bz times epsilon x minus sigma xx bx plus sigma xy by plus sigma xz bz times epsilon z. So I think you can figure out the trend now. The last one would be sigma xx dx, right? Little bit smaller. Plus sigma xy dy plus sigma xz bz whole into epsilon z minus, sorry, epsilon y z, right? So epsilon y minus sigma yx dx yy dy epsilon x. So this will be a f. Okay, sigma dot b cross epsilon. So essentially, what this will lead to, just a second. Yeah, so we can write it in terms of x, y, z, or we can also write it in terms of 1, 1, 1, 2, 2, like that. So 1, 1, 1, 1, 2. So x as 1, y as 2, and z as 3. So depending on how you are framing, how your question is framed, you can use either x, y, z or 1, 2, 3. Okay. Now that we know this force, can we try to calculate it for different conditions? So let's say there is a case where there is interaction between two positive dislocations. Okay. So let's say there's case Now, mind you, we are only talking about dislocations which are parallel to each other here. We will not be studying dislocations which are not parallel, because that they'll be very complex and it will take like a lot of time for us to understand how those dislocations are framed and all that. So we'll only be talking about dislocations which are parallel to each other here, and so that it's simpler for us and we don't have to talk about like a 3D case where we dislocations will be moving in a particular direction. Only in 2D, where we'll see only glide. Actually, not even 2D. We'll be only like concentrating on the glide part, not even on the climb part. So it will just be a glide force that we'll be trying to capture right now. Okay. So dislocation gliding because of the presence of another dislocation. Okay. So let's say we have two positive edge dislocation. Okay, I wrote dislocations. Edge dislocation. So what do we mean by two positive edge dislocations? Means that both of them will have the same sign, or both of them will be like this. Okay. So let's say they are separated by x and y in x and y directions. Okay. This is my dislocation 1, this is my dislocation 2. So the glide and climb force for this dislocation, for these two dislocations, can be written. So I'll write the final expressions only. There's no need to like go through each and every step. Okay. So how am I calculating this glide and climb? Essentially, what we will do is we will try to capture this glide in the end, because we are only concerned with glide. We'll capture the glide with respect to each unit moved in the x direction as a function of y. Okay, so we'll be capturing 1y, 2y, 3y in the glide plane. Okay, so we will have an expression something like this. One second. Yeah. So F will be equal to sigma yx. Let's add. Yeah. Sigma yx times bx and epsilon z. Now I'm not writing square here, I'm writing 2, okay, like dislocation 2. Don't think that is square. While on the y we'll have sigma xx, like all other terms will become 0, okay. So bx, let me not write here, because otherwise it will be confused. And epsilon z. So all other terms will become 0. And in z direction we'll have just 0. So this is my fx, which is the glide force. This is fy, which is the climb force. Okay. So if we simplify and solve for glide, because we are only concerned with glide, my fx will be equal to plus or minus gb square divided by 2 pi 1 minus lambda into x square minus y square divided by x square plus y square whole square. Okay. So this will be my expression. Okay. why am I talking about plus or minus? Essentially, when both dislocations will have the same sign, it will be plus. So when both dislocations have the same sign, we are going to have positive, plus, and vice versa. When dislocations have the opposite sign, it will be negative. Okay, so that's why we say plus or minus. Now, essentially, if this is the expression that we will get for glide, now what happens when they are on the same glide plane? When dislocations are on the same glide plane, then y will become equal to 0, and my final expression will become something like f is equal to gb square 2 pi 1 minus u times. So x into x square will become x cube, and the denominator will have x squared squared, so x to the power 4. So it will be times 1 by x. Okay, let me not write multiply here, just so that you don't get confused. We'll write dot. Okay. So again, positive when dislocations are of the same sign, negative when dislocations are of the opposite sign. Okay. So this is my expression. So essentially, how this will look in the, like if we try to represent it in the form of graph. So if we plot this as a function of, like, x as a function of y, so f is here and x as a function of y. If I'm plotting, let's say this is y, 2y, 3y, 4y, this is minus y, minus 2y, minus 3y, and so on. Okay. So at 0, at x is equal to 0, it will be equal to 0, right? And at y is equal to 0 also it will be 0. So x is equal to y, it will be 0. And x is equal to minus y also, it will be 0. So these 3 points are like fixed points. We'll have 0 at these points. But on the right hand side of 0, we'll have a drop, right? When they are both of the same sign, we'll have a drop, right? So we'll have something like this. But on the left hand side, we'll have a rise. So these two will be fixed. After this, the value just increases and then plateaus off, and then just goes back down to a straight. You can move it a little bit down like this. On the negative side, it will the same thing will happen. It will just plateau and just move. Okay. So this is when both are of the same sign. So what can we note from here? The stable and unstable equilibrium positions. So when they are of the same sign, what will happen? So this is my one dislocation and this is my other dislocation. So between this first dislocation and second dislocation, let's say this first dislocation is influencing the second dislocation, there is a region of 45 degree around it, okay? Because at 45 we are seeing that like x is equal to y, right? That region, x is equal to y, that line. around in that region, what we'll see is that, so if this is my, sorry, actually I have not drawn it correctly. Yeah, so this is my one dislocation. Sorry. Yeah. So there will be a 45-degree line, right? Within that region, if it is within this region, then the dislocation will be in stable equilibrium, right? Because you can see that within this region, the dislocation will tend to stay where it is. So within this region, let's say I shade this region. Stable equilibrium. Wait, is my screen visible? Okay. I just thought screen it. Yeah, so within this region, it will be stable equilibrium. Outside this region, outside this 45-degree channel, it will be unstable. Okay. So this is how you are defining. So you can also predict this based on like what kind of energy they are representing, right? So if there are two like dislocations, if they are of the same size, if they are like dislocation, and they are far away from each other versus they are close to each other. So if they are close to each other, their Burgers vector will add up, right? So if they are close to each other, their Burgers vector is 2b. If they are far away from each other, their Burgers vectors are b each, right? So the energy for this case will be G, sorry, 2GB. Okay, G times 2B square. While energy for this case would be G times B square plus G times B square. So this will be 2GB square. This will be 4GB square. So when they're near, the energy is more. Right? So what will happen? The dislocation will tend to what? They'll tend to stay away. So dislocation will tend to, actually, did I draw it wrong? 1 second, let me just check. Yeah, so they will tend to stay away. This is correct. So they will go and sit here at this place. It will tend to stay away, but at that 45-degree place, it will go and sit at that 45-degree place. Okay. When they are of opposite signs, what will happen? Now, if you draw the dislocations in a similar way, you have one dislocation like this, one dislocation like this. The other way, you will have two far away dislocations. So here again, you will have energy equal to 2GB square. But here, the Burgers vector will cancel each other out, so energy will be equal to 0. So since this is higher, what will happen? the dislocation will attract each other and annihilate each other. Okay. Okay. So here, if the dislocations, this is my 45-degree line, if the dislocation comes in front, like here, in this region, here, it will get pushed outwards. So it will go and sit just outside this 45-degree line. So this is where the stable equilibrium will be. Because this is where it will get pushed from both the sides. It will be stable. Here. While here it will be unstable. Okay. So this is for interaction between two positive edge dislocation. Okay. Now, what about interaction between screw dislocations, which are parallel? Let's take another case. I'll not do the whole process again. This is the exact same thing, but between two screw dislocations which are parallel. So I'm only considering parallel dislocation. So again here we'll be only talking about parallel. So what will happen? Here the glide force Fx will be equal to, similar to the last time, G B1 B2 divided by 2 pi of x divided by x square plus y square. Okay. Again, so when they are of the same sign, they will repel each other, just like how in edge dislocation they repelled each other. They want to sit far away from each other. And when they are of the opposite sign, attract. So here, what do we mean by sign in screw dislocations? Whether they're parallel or anti-parallel, okay? Because screw dislocation as such, their sign is defined by how we have created the screw dislocation, right? So whether they're parallel or anti-parallel will define whether it's, so just a second, okay, whether they will repel or attract. Okay. Final case would be when you have an edge and a screw which are parallel to each other. So as you would have guessed, there will be no force acting because edge and screw essentially cannot interact with each other. Now why that is so? Why can't edge and screw interact with each other? Why can't edge and screw dislocation interact with each other? Because essentially screw has a shear characteristics while edge does not have that kind of characteristics. What does edge have? Edge has a tensile compressive characteristics, right? Above and below the edge dislocation, you will see tensile and compressive stresses. While screw has more of a shear characteristics. So their forces will not align with each other. They will not act with each other, right? So it will become 0, 0, 0. Essentially, no force will be acting on screw dislocation due to edge dislocation and vice versa. So next, let's move on to image force. Okay, the concept of image force. Actually, let me write down this before I move on. No force acts on screw dislocation due to edge dislocation and vice versa. Okay. So now let's talk about image force. So essentially, why we are talking about image force is because supposedly you have a dislocation near a surface. What will happen is that dislocation will go out and leave the surface. Okay, it will go out outside the surface and it will just leave it. Why that is the case is because essentially, like, a dislocation does not want to sit near a surface. It wants to move out, free itself of the energy that is associated with the surface. Now, this can be observed if there is, say, a dislocation acting near a surface, something like this. Let's say there's a dislocation acting near the surface, something like this. Okay, and you have dislocation here. What will happen is the dislocation will move out as a consequence of it being near the surface. So, in order to map a force associated with this dislocation, what we will do is we will create an imaginary dislocation. We place an imaginary dislocation outside the surface at a distance equal to the real dislocation. Okay. So what we'll do is essentially create a dislocation here, which will be at a distance, say, d from the surface. Okay. So equal but opposite dislocation. Okay. And then we can find the energy associated with this dislocation and how much energy is required for this dislocation to move out. Okay. So let me just write down what are the steps. So essentially, an imaginary dislocation is placed outside the surface. The imaginary dislocation is placed outside the surface at a distance equal to the real dislocation. Okay. Just a second. Yeah. An imaginary dislocation placed outside the surface at a distance equal to the real dislocation. Then this dislocation would have the same magnitude but opposite sign. So essentially what we are doing is we are trying to annihilate this dislocation, right? So we need to have an equal but opposite dislocation. sorry, would have the same magnitude but opposite sign. I wrote same sign. I just lost internet for a second. Sorry. Yeah. Okay. The imaginary dislocation would have the same magnitude but opposite sign. Then attractive force is acting on the dislocation, right? Because they have to attract each other so that it can pull it out. And finally, it is only experienced by dislocation near the surface. Not for dislocations within the. Okay. So what are these values for these dislocations? So I can give you the final expression for both edge and screw case. So for edge it will be minus GB square divided by 4 pi 1 minus nu times 1 by d. So d is the distance from the distance from the surface. So this is for edge. Now for screw, the expression would be exactly same, just that you will not have 1 minus u in the denominator. So as you can see, that the expressions are exactly same, just that we don't have that 1 minus nu term in the denominator. So only if the Fx is greater than the lattice resistance, then only we will see some motion in the dislocation. Otherwise, there will be no motion. Okay. Also, you can see that there is negative sign for Fx, right? That signifies the dislocations are of opposite sides. Okay. So this is about image force. Now let's come to the last topic for today, which is partial dislocations. Okay. Let's quickly go through this. So partial dislocations are something that is usually observed only for FCC crystal. You don't see these kind of dislocations in other types of crystal. Like you will see them, but like very rarely. But in FCC, it is very commonly observed. Okay, so essentially for any FCC lattice, right, most of the dislocations will be moving in 110 plane. Okay, for any FCC, we have dislocation Burgers vector will be 110. Okay, so it will be something like a by 2 1 by 0. That will be a dislocation motion. Okay, direction of dislocation motion. And FCC has ABC ABC sequence. So this is something that you can just remember. Now this is required for what I'm going to talk about. Okay. ABC stacking sequence. Not sequence actually. Let me just write. Okay. So this is for ABC, FCC, right? So what will happen is when dislocation tries to move in the 110 direction, okay, some family of 110, okay, it will try to move. It encounters another direction, another Burgers plane that is much lower in energy, okay. Now the dislocation is along the 111 plane and it is moving in 101 direction. What happens if it encounters another direction which is again perpendicular to the 111 plane, but is much lower in energy as compared to 101, and that plane is 112. Okay, so essentially what will happen is if the dislocation is along, I'll write it in terms of a family that actually can exist. So 111 plane, sorry, 111 is the plane, and the dislocation will be moving in the direction 101 bar. Okay, so I'm writing a proper dislocation direction. So it can also move along 112 bar and 211 1 bar 1 bar. So this is 112 bar and then 2 1 bar 1 bar. This is because the energy associated with this plane, with this direction, the two directions, is lower than going in this one direction 101. Okay. Now, how am I writing these two particular low energy paths? Is because the Burgers vector of 101 bar will be equal to the Burgers vector of the sum of the Burgers vector of 112 bar plus 211 bar, 21 bar 1 bar. Okay. Now, if you want to calculate the energy associated with dislocation, what do we have to do? We have to do GB square, right? So GG, let's say it's cancelled. So essentially, if I say B1, say this is B1, 101 is B1, B1 square is equal to, what is B1 square? A by 2, so it is A by 2, 101 bar. So 2 divide, so 1 by root 2. So 1 by 2. So B1 square will be 1 by 2, right? While B2 square plus B3 square will be equal to what? So this will be 112. So 1 by 6 plus 1 by 6. This will be 1 by 3. So as you can see that B1 square is greater than B2 square plus B3 square. So therefore the dislocation would tend to move in the lower energy path, and it will essentially create a fault known as stacking fault. Okay, so there is a stacking fault which will be created, which will have an HCP kind of configuration. So essentially your dislocation here, if it was B1, this was having FCC configuration. After it splits into these two partials, okay, with B2 and B3, okay, so there will be this faulted region. Which will have HCP characteristics. Now this is your leading and this is my trailing partial. So these are leading and trailing partials. Again, you don't need this information. I'm just giving you extra information. So yeah, like FCC had ABC stacking sequence. HCP has AB sequence. Okay, this you can just keep in check. So essentially, your faulted region will have AB stacking sequence, and the dislocation will break. So what we need to learn from here is the dislocation can only break into partials only if the sum of the partial dislocation, the Burgers vectors in the partial dislocation, is equal to the final Burgers vector which the dislocation was supposed to move in, and the energy is lower for the partials. The sum of the energies for each of the Burgers vector is lower than the original Burgers vector that the dislocation was supposed to move. Okay. Only when these two conditions are met, then the dislocation would move in partial space rather than moving in the real space. Okay. Let me just move this page. We can move to problems. Okay. Just give me 1 second. Okay. Yeah. So let's come to the problems. Coming to the first problem. Which of the following statements are incorrect about critical resolved shear stress, CRSS? So they are asking which are incorrect. Okay. So we'll see which and all are incorrect. So for polycrystalline material, it is termed as tensile stress. That is incorrect. So this one is correct. CRS is a material property, that is correct. CRS is equivalent for a single crystal is termed as yield stress. Okay, yield strength, we talked about it. Just a second. Yeah. So CRS is equivalent for a single crystal is termed as yield strength, that is correct. CRS is changes with alloy composition and temperature. That is also correct. So the only option which is incorrect is the first one. So now, second question, they are saying consider the following FCC dislocation reaction. A by 2, 0, 1 bar 1 gives A by 6, 1, 1 bar 2 and A by 6, 1 bar 2 bar 1. Which of the following statements are correct? Given dislocation reaction is energetically favorable. So for it to be energetically favorable, the energy for like B1 square should be higher than B2 square plus B3 square, right? So I have already shown you, again you can see that B1 square will be equal to how much? A square divided by 2, right? While B2 square plus B3 square will be A square by 6 plus A square by 6, or that will be equal to A square by 3. So therefore, this is correct. Then they are saying that the dislocations that they have given, A by 6, 1, 1 bar 2 and A by 6, 1 bar, 2 bar, 1 bar are the partial dislocations. That is correct. Right? And the above dislocation dissociation reaction will result in a stacking fault. That is also correct. Final option, above dislocation dissociation reaction can never take place. That is wrong. Why we are saying that this can take place is because if you see the Burgers vector, if you add the Burgers vector on the right hand side, you will get the Burgers vector on the left hand side, right? Because you can see here 1, 1 and minus 1 for the first one. That will lead to 0. Then let me use a different thing so that it's clear. Minus 1 and minus 2, if I sum, I'll get minus 3. Minus 3 by 6 will be minus 1 by 2. So this is correct. And the third one, 2 and 1. So that will be 3. 3 divided by 6 will be 1 by 2. So here it is 1 by 2. So that is also correct. So the sum is exactly right. Therefore, this dislocation can take place. So therefore, the last option is incorrect. Okay. Next question. A perfect dislocation having Burgers vector a by 2 1 bar 0 1 dissociates into a by 6 2 bar 1 1 and a by 6 1 bar 2 partials. On which plane of 111 family these partial dislocations lie? Okay. So essentially they are asking where will this lie? How will we find that out? How will we know which dislocation, where will the partials lie? That is a very simple rule, right? For any dislocation or dislocation partial to lie on a plane, the dot product should be equal to the dot product between the dislocation direction and the normal to the plane. The direction which is normal to the plane should be 0. Why? Because they should be perpendicular to each other. Correct? So if dislocation lies on the plane, the dislocation normal should be perpendicular to the dislocation plane. That is what we have to ensure. So essentially we need to have 2 bar 1 1 and the dislocation line, so normal to the dislocation plane should be equal to 0, and also 1 bar 2 and dotted with xyz should also be 0. Okay, so both of these lead to y plus z equal to 2x. This one also will lead to, no, this one will lead to x plus y equal to 2z. Okay, so these are the two expressions we have. We have 3 unknowns, 2 expressions. So essentially we'll have to put the options in this equations and see which one satisfies both the equations. So does 111 satisfy? Yes, 111 will, y plus z will be equal to 2x and x plus y will be equal to 2z. That will satisfy. Will 1 bar 1 1 satisfy? No, right? Because 1 bar will make it minus 2 on the right hand side, y plus z will be plus 2, so that will not satisfy. 1 bar 1 1 bar, will it satisfy the first equation? 1 bar 1 1 bar, no, right? Because on left hand side it will be 0 here for the first equation, while right hand side will be minus 2, and 1 1 1 bar, that will also not satisfy because on left hand side it will be 0 again and right hand side will be 2. So only first option 1 1 1 will satisfy the given problem. Okay. So coming to the next question, below figure shows 2 different configurations for a set of interacting edge dislocations. So they are asking which of the following are true for these interactions. Okay. So they have given a 60-degree angle, 2 dislocations which are present, and in configuration 2, 2 dislocations of opposite sides. So first one has 2 like dislocations, this one has 2 opposite dislocations. So which are the correct options? Dislocations are in stable equilibrium in configuration 1. There is no net glide force on either dislocation. That is wrong, right? They are not in stable equilibrium in configuration 1. They are in unstable equilibrium. The dislocation will try to move in this direction and try to come to that 45-degree position. It will try to come to that 45-degree position. So it is not in stable equilibrium. There is a net attractive force between dislocations in configuration 1. That is correct. There is a net attractive force between dislocation and configuration 2. That is wrong. They will try to push each other far away. So that will be not correct. Dislocations are in stable equilibrium in configuration 1. Again, the same option is repeated, I think. So that is again wrong. So only option B is correct. So next question. ABCC single crystal having critical resolved shear stress of 80 MPa was deformed under uniaxial compression. Evaluate the stress required to initiate plastic deformation in the slip plane 112 along 112 along this will be 1 bar 1 bar 1 no 1 bar 1 bar direction. Yeah, this will be 1 bar direction. Right. So if you want to find the uh, what is the stress required to initiate plastic deformation, we would need to calculate. Already tau CRSS is given to us. We have to calculate cos phi and cos lambda, right? So cos phi would be equal to cos phi would be between uh, 110 and 110 and 11 112 slip plane, right? 112. Yes. So this will be on top. It will be 1.1 plus 1.1 plus 2.0 divided by denominator will have root 2 and root 6, right? So this will be 2 divided by root 6. So let's just keep it like this only. Cos lambda will be equal to cos lambda will be equal to 1.1, sorry, plus minus 1 dotted with 1. So this is also minus 1 actually. Yeah. Minus 1.1 minus 1.1 plus 1.0 divided by root 2 and root 3. Okay, so this will be equal to minus 2 by root 6. Okay, so this was not root 6, this was root 12. So actually let's solve it. 1 by root 3. So now if I write sigma is equal to tau CRSS divided by cos phi cos lambda, we can calculate, right? So let me just calculate. CRSS is given as 80. So let me just calculate. So I am getting negative of 169.7 MPa. Okay. I hope everyone has got the same answer, whoever is trying. So essentially, we are dividing 80 by cos phi and cos lambda, which are given as 1 by root 3 and minus 2 by root 6. Okay. So we'll get 169.7 as the final answer. Negative of that rather, because cos lambda is negative. Okay. We just check the answer once again. Not made any mistake. is correct answer. Okay. Next question. Evaluate force per unit length in case of two parallel positive edge dislocations lying on the same plane, having Poisson's ratio 0.3, shear modulus 40 GPa, Burgers vector of magnitude of Burgers vector is 3 Armstrong, and distance between dislocation is 1000 Armstrong. Okay. So they have given us all the values. We just have to use the expression to find the final value. So essentially, what is our expression? F is equal to GB square 2 pi 1 minus lambda, sorry, 1 minus mu, right, times x square minus y square divided by x square plus y square whole to the power 4. Sorry, whole square. Yeah. But they have told that y is 0, right? They are lying on the same plane. So y is 0. So if I put y is equal to 0, then it will become GB square divided by 2 pi 1 minus mu x cube divided by x to the power 4. So 1 by x. So this is what I have to substitute and find the final answer. So let me just substitute and find the final answer. They have given us all the values. G is 40 GPa. Burgers vector is given as 3 Armstrong. Distance between dislocation is 1000. So x is 1000. B is 3. Poisson's ratio is 0.3. So all the values are given. So let's just calculate. I'm getting around 8.18. That's the correct answer. 8.18 into 10 power minus 3. So yeah, there is an option. Newton per meter. So the closest answer to that is 8.2. That is the correct option. Right. Okay. So move on to the next question. The yield stress is minimum when where phi is the angle between the tensile axis with the normal to the slip plane. Lambda is the angle between tensile axis and the slip direction. So yeah, they have given the same thing. So they are asking when is yield stress minimum. So when slip planes are oriented close to 45 degree with respect to axis of loading, that is correct. Schmidt factor is maximum. Yes, M has to be maximum for yield stress to be minimum. Right? If you remember the curves I had shown. Respect to orientation is equal to 0, orientation equal to 90. So this was the curve, right? So yield stress was minimum at 45 degree. So Schmidt factor was maximum. Phi plus lambda was 90 and phi and lambda were both equal to 45. So all the options are correct. All the options are correct. Next question is, two edge dislocations have a stable equilibrium. When do they have stable equilibrium? When they are at positions x is equal to plus or minus y for opposite sign dislocations. Correct? Right. For oppositely signed dislocation, they have to be at plus or minus y. Right? Then only they'll be at stable equilibrium. They are far away from each other for same sign dislocation. No, that is wrong. They are at positions plus or minus x or y for same sign dislocation. Wrong. They are stacked one below the other for same sign dislocation. That is correct. So when they are at 45, they'll try to come together. They'll stack one below the other. That is correct. Next question. Mark the correct statements. Image dislocation for a left hand screw, dislocation at minus x near a free surface is left hand screw at plus x. That is wrong. For left hand screw, it should be right hand screw, right? Because I told the hand changes, the parallel anti-parallel kind of image, right? So image, so next option, image dislocation for a left hand screw at minus x near a free surface is right hand screw at plus x. That is correct. Then image dislocation for a left hand screw dislocation at minus x near a free surface is left hand screw at plus x. That is again wrong. And image dislocation for a right hand screw at plus minus x near a free surface is left hand screw at plus x. That is correct. So these two options are correct. Okay. So now moving on to the last question. In FCC crystal system, if a dislocation is A by 2 1 1 0, like it dissociates into A by 6 2 1 2 bar 1 1 and A by 6 1 bar 2 1 bar. On what plane this partial dislocation lie if plane is from 1 1 1 family of plane? Okay. So this is the question. Now let's try to see where the plane would lie, right? So first things first, the plane should be like the two dislocation partial should be lying on that plane, which means that 2 bar 1 1 and normal to the plane x y z, the dot product of this should be equal to 0, and 1 bar 2 1 bar and the dot product of x y z should also be 0. So x y z represents the plane normal, plane normal direction, right? So if I see here, it will be 2x equal to y plus z and x plus z equal to 2y. So these are the two equations which has to be satisfied. Now from the various options, first one will satisfy, right? Both the equations. Second one 0 0 1 will not satisfy. Third one 1 1 0 again will not satisfy, and 1 0 1 will also not satisfy. So this is the final answer. Okay. I actually have one more question. Let me just see if I can find that question. Yes, that is a very good question. I found the question. Let me just bring the question here. Came across this question. Let's say this is our 11th question. Okay. They are saying determine the tensile stress that is applied along the 110 direction to cause slip on the 111 and 0111 system. The critical resolved shear stress is given as 50 MPa. Okay. So they have given us the loading direction as 1 bar 0, slip plane and direction as 1 1 bar and 0 1 bar 1. They have also given us the critical resolved stress, which is 50 MPa. So the angle between the, so we can find cos theta and cos phi, right? First, cos phi will be equal to cos phi is equal to 1 1 1.1 plus minus 1 dot minus 1 plus 0.1 0 or minus 1 divided by root 2 dot root 3. So this will be equal to 2 by root 6. Now the angle between the loading axis and the slip direction, loading direction and slip direction will be equal to 1.0 plus minus 1 dot minus 1 plus 0.1 divided by root 2 dot root 2. So it will be 1 by 2. Right? So now we have cos phi cos lambda. So tau CRS is given to us, that is equal to 50 MPa. So sigma is equal to tau CRS divided by cos phi cos lambda. Right? So that is equal to 50 divided by 2 by root 6 to 1 by 2. Okay. Essentially it will be 50 times root 6, right? Let me just calculate. So 50 times root 6 will be 122.47. Okay. So the second half of the question, they are asking a tensile stress along 1, 2, 3 was applied in an FCC single crystal. Rank the slip system according to the Schmidt factor. So they are saying if the tensile stress was acting along 1, 2, 3, then you have to rank each of the slip system according to the Schmidt factor. Okay. So this is A part. This is B part. So how do we rank this? So we know that there are 4 slip planes for FCC, right? So for 111. So essentially, I'll show you for one slip plane how do you do it. Then you can continue on for different slip planes. Okay. So let's just divide it into motions. Okay, slip plane, slip direction. Then you have, okay, let me just, okay. This is my slip plane, slip direction. Cos phi, cos lambda, okay, and Schmidt factor, that is M. So first we'll have 1, 1, 1 plane. Okay. So there will be 3 slip directions in each plane for FCC, right? So 0, 1 bar, 1 would be one slip direction. So essentially you will have to find each slip plane slip direction and test for each one. You will have 1 bar, 0, 1, and then you will have 1 bar, 1, 0. So these are the 3 slip direction for this. So your cos phi will be same because it's the same slip plane. 6 divided by, now I have these values. Okay, so I'll just write it down, but essentially I want to show it to you for one particular case how you will do it, and then for remaining slip planes and slip directions you can calculate. Okay, I'll give you the other slip planes, but I'll not give you the other slip directions. Okay, so this one will be 1 by 2, sorry, root 2 root 14. Two root 7. Then this one would be 1, so 2 by 2 root 14, so that will be 1 by root 7, and the last one would be 1 by 2 root 7 again. Okay, so essentially your Schmidt factor for the 3 cases would be 3 divided by 7 root 6. Okay, 6 divided by 7 root 6, and 3 divided by 7 root 6 again. Now similarly you can go ahead and find the same things for the other slip planes. So I'll give you the slip planes. You have to find the slip directions yourself and try out this problem. Okay. In case you're not able to solve, we can try it in the next class sometime. But this is how you're supposed to do it. So then try for the other 2 slip planes also. I'll just write down the slip planes here. 1 bar, 1, 1. One bar. Okay. So similarly, you'll have each slip plane will have 3 directions. You have to find for each case, and then you have to find Schmidt factor for each case, and then you have to rank them according to decreasing Schmidt factor or increasing Schmidt factor. Just rank them. Okay. So that's what you have to do for each case. I hope you have understood how to do it. So you don't have, like, I don't have to show you each case, but you have to do it like that. Okay. Find the dot product between 1, 2, 3, because 1, 2, 3 is the tensile stress, the direction they have given, and then cos phi, cos lambda you can find using that, and then find individual Schmidt factor by multiplying cos phi and cos lambda. Okay. So yeah, with that we'll come to an end for today's discussion. I hope you have all understood the concepts, the various concepts that we have discussed today, and all the problems that we have discussed. In any case, if there are any doubts, we can continue that in the next class. You can also ask me to re-explain some concept that you have not understood in the next class again. With that, we'll end today's lecture. I thank everyone for listening.